Okay, hi everyone. I know that it is very late and I know that everyone is very hungry, so I will try my best to finish my talk earlier. Oh, my name is Lei Yang from the Hong Kong PolyU. Yeah, this is my honor to introduce our recent work. My work is titled Analog on-tag hashing towards selective reading as hashing primitives in Gen2 RFID systems. Okay, firstly, I would like to introduce a little about our background and our motivation. Okay, according to report from the IDTech, 18th billion tags has been sold this year so far. Okay, it's really a large number. And the typical RFID system composed of three components. The first component is the reader, the second component is the tag, and the third component is the air protocol. Okay, there are so many standards about the air protocol. And among of these, the most widely used one is the EPC Gen2, okay, proposed by the EPC Global. By the way, EPC means the Electronic Product Code. And the air protocol, Gen2 air protocol, is based on the framed Aloha protocol. For example, the reader divided the reading procedure into many time threads. And each tag is randomly select time threads to reply their ID. If there is a collision, and it will restart a new frame, and this procedure continues until there is no collision. We conduct a experiment on the efficiency of the Gen2 protocols. It's called as a Q-adaptive. We can see that it looks less like that Q-adaptive is not so efficient, because when the number of tags increased is over than 20, in the 30, and the reading rate is defined as the number of tags read per second. We can say that reading rate introduced 80% drop. Okay, and you may be wondering why we don't use the more complex communication mechanism like the FDM, CSDM, or CSMM. Okay, unfortunately, it don't work in the RFID system. Okay, this is RFID tag. They are tiny, cheap, and battery-free. They cannot support the complex communication mechanism. And most important, the tags cannot hear with each other. So how to speed up the reading procedure? 10 years ago, the hash-enabled protocol, HIP, was the purpose. Okay, the basic idea of the HIP is to let the reader and the tag share a hash function and consider the collisions as being informative. Okay, specifically, the reader divided the reading procedure into the many time slots, and each tag selects a time slot based on the hash value of its ID and a random number. The random number is broadcast by the reader. And in the time slot, each reader only transmits a 1-bit signal to show its existence instead of the whole EPC number. In the end of the frame, the reader abstracts the result into a present bitmap. Each bit in the bitmap corresponds to a time slot. If there is a reply, the bit is set to the 1. If there is no reply, the bit is set to 0. So what can we do with the present bitmaps? There are actually a large number of applications has been deployed in the last decade. For example, we can estimate the total number of tags by observing the number of ones or zeros in the bitmap. And we can also detect the missing detections. For example, in a closed system, for example, like the warehouse, we know the EPC advantage, so we can generate a perfect bitmap. And by comparing the instance and the perfect bitmap, we can infer which tag is missing. For example, if this tag is supposed to reply at this time slot, but if there is 0, this tag must be missing. Okay, we can also conduct the continuous reading or the data mining. There are so many applications. The HIP is advantageous in 2 aspects. Because first, it does resolve the collision, so it can boost the performance significantly. Second, each tag only sends the 1-bit signal, so the privacy is well preserved because you cannot identify the object through 1-bit signal. And unfortunately, after 10 years of enthusiastic discussion about the opportunities the heap provide, the reality is beginning to bite because it requires each tagger equipment with a hash function. Okay, this table shows the recent hash function designed for the RFID tags in the community provided by the community. From the table, we can see that even the most lightweight hash function requires the 1,000 gates. Okay, they are so complex and cannot supported by the tag. And there is no hint that in the near future, tag will have a hash function. Okay, this makes the help like the 10-year untouchable marriage in practice due to lack of the hashing functionality. This work, we introduced a group of the hash primitives over the Gen2 RFID systems without any modification on the hardware or software. Okay, before present our design, I would like to introduce some background about the Gen2. There are 3 core functions specified in the Gen2 standard, and we will use them to design our hash primitives. Okay, the first function is a memory bank. Gen2 specifies a simple tag memory model. Okay, each tag contains the 4 types of the blocks. We call that a memory bank. The first 3 memory banks are used to store the password, EPC, TID, and the last one is reserved for the user-defined data, and we will store the data in this memory bank. The second function is a select reading. Okay, the reader can broadcast a select command. The command contains a bit mask. Only the tags matching the bit mask will reply in the upcoming reading procedure. And the third is a trunking reply. We can initiate a special select command for 1-bit reply. Okay, and in the paper, we proposed 3 hash primitives. The first is the hash function. We call it a hash function in order to distinguish the real hash function. And the second is a hash table function, and third one is a hash operator. Okay, this is the design of our hash function. This figure shows the memory structure of the tag. In the first memory bank, we store the EPC. We calculate the real hash value of the EPC using the real hash function. The real hash function may be the SHA-1 or MD5. And we then store the real hash functions in the third memory bank, the user-defined memory bank. Okay, and all the calculations and storing are performed offline in advance. Okay, our hash function accepts 2 inputs. The first input is a random number. The second input is the dimension. The dimension determines the length of the output. Okay, for example, in here, the output of our function is a bit string starting from the R and ending at R plus L minus 1. Okay, actually, our hash value is just a portion of the real hash function. And our hash function is determined by the EPC, and EPC, random number, and the dimension. Okay, the traditional heap output produce the present bitmap. Actually, our approach can produce a present table. In each entry, the member indicates how many tags hashed into this entry. Of course, we can easily to convert our hash table to the present bitmap. Okay, this shows the design of the hash table function. We build a hash table entry by entry. Each entry corresponds to an independent reading procedure. For example, we want to build the third entry. Okay, the third entry means that the hash value equals 2 because the table index indicates the hash value. And then we broadcast a select command to select this select command contains the bit mask with the hash value of 2, so that only the tag whose hash value equals the 2 will reply in this reading procedure. Okay, because we have the 4 entries, so we will start the 4 entry reading. Okay, in each entry reading, we have the two select commands. The first select command is used to select the text based on the bit on the hash value, and the second select is used to for the 1-bit reply. Okay, we also traditional help usually requires multiple bit maps to reduce the false positives. Okay, and they of course they must to acquire multiple bit maps. In our proposal, in our work, we introduced the Tash operators. We allow the system to perform the set operations on tag, okay, in the physical layer, so that only one bit hash table is enough for us because we perform the set operations on tag. And this is our implementation. We design our hash primitives based on the Gen2, but implement it use LRP. I must claim that there are different protocols. The Gen2 protocols is used for the communication between the reader and the text, and the LRP, the low-level reader protocol, is used between the client and the reader. We use the LRP is a driver protocol. We use the LRP to control a reader to broadcast the Gen2 commands we required. Okay, the right shows the sampled XML file defined by the LRP. We implement our system use Cortex RFID devices. We attach the 300 tags in front of single RFID antenna. Okay, firstly, we investigate because our design totally depends on the 3 core functions specified in Gen2. So firstly, we investigate the Gen2 compatibility. Okay, of course, the 20 types of tags and 4 types of the readers. In the form table, we can for example, from the table, we can see that we use the memory bank 3 to store the real hash function. From the table, we can see that except one read-only tag, all other tags can support the memory bank 3. So in total, current commercial Gen2 system will support our functions that we require. Unfortunately, not all the readers can support the trunked reply. Okay, of course, we hope that we work can encourage the manufacturers to upgrade their firmwares for the full compatibility. Okay, we evaluate the hash value in terms of the randomness. Randomness is an important metric for hash function. Okay, we generate the 300,000 or 100,000 hash value. And the left figure shows the distribution of the 0 and 1. The right figure shows the randomness test result. We can see that our function has a good quality of randomness. In the third, we evaluated touch table functions in terms of the balance and the efficiency. We know that a good table hash function can assign a key into a bucket equally. So we require the balance. Okay, from the figure we can see that the left figure shows 60 in the hash table. We can see that the number of the tags is almost equal. And the right figure shows the garrison time with trunked reply and without trunked reply. And we can see that if we use a trunked reply, it will introduce the 60% drop of the overhead. And lastly, we evaluated the tag operator. And we show the performance of a Tash OR over the 2 tables. Okay, we have 3 cases. In the first case, we just read them all. This is a very naive approach. And in the second case, we create 2 hash tables respectively and collect them respectively and conduct the OR operation in the server. And in the third case, we create the final hash table with the set operations proposed by our system. We can see that our Tash operator can introduce a 99% drop of the overhead compared with the reading all. Okay, if you conduct more operations, I think the drop will be larger. And in our paper, we also conduct the application studies, 2 application studies. We estimate the tag number, and we also detect the missing detection. If you have any interest, please refer to our paper. Okay, in conclusion, in this work, we design a hash function over the existing commercial Gen2 tags without any hardware modification. And we design a hash table function over tags. And we also designed 3 Tash operators to perform the n-chain-wise set operations over multiple Tash table on tag in the physical layer, which offers a one-stop acquisition solution. We hope that we work can revolve all the applications proposed in the last 10 years. Thank you. That's all.